The next stop on our algorithm analysis odyssey is to figure out how to analyze recursive algorithms. And I want to do this with two lectures. So I want to spend this lecture just talking about if you have a recursive algorithm, how do we come up with some way of characterizing the running time? And we're going to see that when we do that, the characterization we end up with isn't something that's amenable to making a statement like this is big theta of n or this is big theta of n squared. And so we're going to spend the next lecture looking at techniques that we can use to find some way of putting that into one of our familiar asymptotic classes. And one thing I'm going to say right off the bat, and I'm going to come back to this a few times, is that what we're going to see in this lecture turns out to be sort of grueling. And what we're going to see in the next lecture doesn't always help that much. And so if you're looking at this stuff and thinking, wow, there's a lot of tedious algebra here, this might be error prone, that's right, I think so too. Our goal, though, by the end of the next lecture, I guess, is to discover that most of the cases we're likely to see, so most recursive algorithms, fall into one or two familiar categories, which are relatively easy to talk about. And that within a few lectures from now, we will just be able to, at a high level, talk about the running time of recursive algorithms without all of the tedious stuff that we're going to see today. So I guess basically my warning is just don't panic. I want to use this opportunity to go back a bit and talk about the non-recursive analysis that we've been doing. So I think this is the last time we'll see it. I said that before, but I think this is the last time we're going to see these expressions we came up with for those contains duplicate algorithms a long, long time ago. So what we saw was that if we want to analyze an algorithm with the ultimate goal of coming up with a big theta expression, well, one way of doing that would be to count operations one by one. And we also saw, in the meantime, over the last couple of lectures, that it generally doesn't seem to be necessary to do that. That is, we got this expression that was 4n squared plus n plus 2, and we figured out by now that that's just big theta of n squared. So we don't really care that much about that 4. I mean, that could have just as easily been a 5 as far as we're concerned. And if you think back to the analysis of those convex hull algorithms in the last lecture, we were able just to glance at a loop and conclude, well, the contents of the loop are constant, and the loop itself runs for n iterations. Okay, great. So that means that it's big theta of n. We didn't actually have to do any of this tedious analysis of individual operation counts. It's true that when the loop is somehow unusual looking, we have to present some form of justification. So justification like, hey, these two nested loops together somehow still have running time big theta of n, and here's why. But our analysis can be pretty high level. And the reason for that, essentially, is that we've all agreed by now that this operation counting logic makes sense. And so we don't actually have to do it, because we've agreed that, yes, if I count operations, I'm going to get some constant times n squared. And because we all accept that, it's not necessary to actually come up with 5n squared or 4n squared or whatever. And I'm using this opportunity to sort of tie up a few loose ends, or to make sure that we know these loose ends are tied up, because I've addressed this in a couple of previous lectures, but this is a good time to wrap it all up. So we performed the analysis, which produced these expressions using this fictitious architecture. So we decided that analyzing the number of, clock cycles or operations or instructions performed by a real processor, like the one in my laptop or the one in my phone, that would probably not be a good idea, because real processors are not designed for that particular thing to be convenient. They've got other things that they want to prioritize. So we decided that because it turns out constants will be irrelevant, and of course when I first said this we didn't know that yet, but we now know that to be true. Because it turns out that constants will be irrelevant, if we invent our own architecture that is realistic, that is to say it supports all of the operations that we need, and all of those operations require a non-zero amount of time. So for example, if I decide that the plus operation requires one clock cycle or one instruction, and the multiplication operation also requires one instruction, well, maybe it's the case that on your phone or on your laptop, the plus operation requires one instruction and the multiplication operation requires, 5 instructions. But the argument we've been making is that this is still fine, that we can still analyze it with our more convenient fictitious architecture, because we could always say, well, look, really, on your phone or on your laptop, to say that plus requires 1 and multiplication requires 5, those are both constants. We could just assume really that plus requires 5. That is, that all operations require the same constant amount of time, which I guess we could just define to be the upper bound of any operation. And For my money, I would say probably division. If you look at any typical processor and look at integer operations, probably division is going to take longer than multiplication or the plus operation, whatever. So the idea was, well, if we know that ultimately the processors with which we are familiar, so the architectures that we tend to use, which tend to be von Neumann architectures and tend to have either an instruction set that allows instructions to go directly to memory or a reduced instruction set where loading from memory is separate, like we can make certain assumptions about the way processors work. And in general, they are all members of this big family of processors that fall into the random access model. As long as we design our architecture to be realistic, to be faithful to that model, the fact that things take one operation isn't really a big deal. Okay, so there's my spiel again about why the fictitious architecture makes sense. And the reason it makes sense in our context is that all we care about is that big theta expression. That's the key point. Obviously, if we cared about showing that a particular function was asymptotically approaching a certain value, so this f1, for example, asymptotically approaches 4n squared, well, that might be a bit of a harder sell because obviously that 4 might depend on the specific contours of an architecture. But we're not doing that. Instead, we are just talking about these big theta expressions where all we care about is the function of n. We don't care too much about the constants. And as a result, I think I've been able to argue successfully that what we come up with our fictitious architecture is close enough, that is, up to these constant factors, it matches what we can expect to see on a real processor, that we can use it for our analysis. And I think that if you want justification for that, so one way to justify that would be empirical analysis. It would be to perform an experiment. And the timing experiments that we've already seen, so for example, the ones in the first lecture, actually do seem to match up to this idea, which is we do notice that if I run these algorithms on a real processor, that we do indeed see worst case n squared performance. The timing experiments that we perform do seem to validate these conclusions, at least to the extent that they can. We know that timing experiments don't really prove anything, but they do help us understand that this connection that I'm claiming exists here can't be completely made up. Like there has to be some logic to it. Okay, so that's one thing that we've observed. And again, what we can think of now, looking back, is that we don't really need to do operation counting. At the end of the day, the idea of the operation counting is to give us a mental model, but that we usually can skip over a lot of those details. And I'll come back to that when we see some pseudocode in a minute. So basically what I'm saying is we can expect, if I go and implement the 3 algorithms that we came up with in the first lecture, these contains duplicate algorithms, I can expect that on any architecture with which we are familiar, so my laptop or my phone or whatever, that they will actually be big theta of n squared. So it doesn't matter that much that I got a 4 there or that I got a plus 2 there. All that matters is I said it was big theta of n squared and that does seem to generalize to real architectures. And so the reason we do this, the reason we care so much about big theta, is because if I have a bunch of different algorithms for a problem, I want some easy metric by which to compare them. So I want to be able to say, look, this sort and scan algorithm for large values of n, since we know by now that n squared of, or n log base 2 of n is big O of n squared, and in fact, actually, it turns out that it is indeed little o of n squared. Since we know that, we can look at these 3 algorithms and say, well, obviously, the sort and scan algorithm will be the faster one as n becomes very large. That isn't to say that it's always going to be faster, because for all we know, a particular application might be working with a certain value of n. And there is also this other thing that's been hiding in the background. I've mentioned it a couple of times, but because big theta hides a constant factor, I guess it is theoretically possible at least, and this does happen sometimes in practice, for an algorithm's real running time to be proportional to an absolutely tremendous constant times, let's say, n. So think about an algorithm whose running time was something like this. So I don't know, 10 to the 16, or I mean, let's just exaggerate this, 10 to the 100 times n. Okay, well, t of n is therefore big theta of n, and that looks good. It's a linear time algorithm. But think about this for a minute. If n itself is any smaller than this number, well, then t of n is actually going to be bigger than n squared. If I have an algorithm that's a very clean n squared, so or maybe like a really efficient like 1/2 n squared, well, that's actually going to be, let's call that t prime. That's actually going to be a lot faster than my original t, up to values of n around this number, and this is an unreasonably large number. So keep that in mind, that there are obviously places where asymptotic analysis breaks down, where there are algorithms that can slip through the cracks. We can see an algorithm that is apparently linear time, but that turns out to have such a huge constant in front of it that gets disguised by that big theta, that for all intents and purposes, if we go and use the algorithm, it's never actually going to be that fast. And these algorithms do exist. However, generally during our analysis process, we would be able to pick that up. It's true that if I hand you an algorithm, I could prove that it's big theta of n, and maybe deep down I know that actually that comes with a catch. It turns out it's n times 10 to the 16 or 10 to 100 or whatever. But usually when we do our analysis, we can get an impression as to whether or not the constants involved are going to be unreasonably large. So whether or not this constant is 4 or 5 or 7, it's pretty clear to us when we look at our pseudocode whether it's 10 to the 100. So while it's true that asymptotic notation can let us hide details, as long as we're being careful when we do our analysis, we should be able to pick those up. And then when it comes time to compare algorithms, as long as when we did our analysis, understood that the constants involved are relatively small. So if our constants are all, I don't know, let's say less than 10,000 or less than 100,000 or less than 1,000,000. So if the constants are likely to be much smaller than our values of n, then it's reasonable to look at these things and say, well, the sort and scan one is faster. We have to be a little bit careful, but in general, these things make sense. In general, in practice, it is the case that the constants involved in algorithms are things that we can estimate. We can ballpark them to the extent that we know whether they're going to get in the way. And if you ever see an algorithm where there apparently are some constant number of operations being performed that's unreasonably large, you would know to be a bit cautious about using asymptotic notation. Now, suppose that we were in a situation where two algorithms actually were part of the same asymptotic class. So suppose we have this here. So we've got two algorithms that are big theta of n squared, and we want to compare them to each other. We don't just want to pick of the three, pick the best one. Suppose we don't have that third one there. Then the question is, which of these two is faster? Well, obviously the asymptotic notation doesn't help us because they're tied as far as big theta is concerned. Well, in that case, we do have to do something else. We can't use big theta if it's tied. So what do we do? Well, we could compare these functions directly, but we run the risk of accidentally reading into some assumptions we made about our fictitious architecture. So how do we know that this is really going to be just n squared plus 2 on a real processor? And how do we know this is going to be 4n squared plus something on a real processor? We have to be a little bit more careful there. What we're going to see in this course is that it doesn't happen very often. And when it does happen, there are lots of options. The options don't tend to boil down to some general method. It tends to be that we want to tailor the method that we use to the application. So what I might do in this case, for this, if you recall the two algorithms that we're talking about here, these two nested loop algorithms, is I might observe that I derived my improved algorithm by starting with my original algorithm and deleting a bunch of operations. And I think that would be sufficient, just reasoning about it. I mean, if I showed the pseudocode, and I now regret not putting the pseudocode in these slides, if I show you the pseudocode and I observe that this one definitely requires fewer operations, whether that's 2n squared or 5n squared or whatever, then it's easy to justify that this one I should expect to actually be faster in practice. And I could even use timing experiments, if I'm careful about that, to demonstrate that point. So of course there are cases where algorithms are tied asymptotically and we have to try other things. Asymptotic analysis isn't the only method that we should have in our set of tools. However, we'll notice in this course, we are generally comparing distinct algorithms that have different asymptotic classes. And if we design two algorithms with the same asymptotic class, we usually know enough about them to reason about which one should be faster. So if you think back to the convex hull algorithms from the previous lecture, we had one that was n cubed, more or less, one that was n squared, and one that was n log n. And asymptotic analysis is great for showing which one of those is faster. And notice how the analysis that we did could be pretty high level as a result. All right, well, let's talk about this. Here's a function that computes factorials. And remember that the definition of a factorial, so n factorial, is the product of all values from 1 up to n. And remember that means that 1 factorial, let's do n minus 1 times n. So that means that 1 factorial equals 1. Now, I also maintain that 0 factorial equals 1, but I don't need to have an argument about that right now. If you want to talk about that, come to the office hours. For our purposes, this is sufficient, this definition of the factorial. So although the factorial is defined this way, I mean, for all we know, there might be some other clever way of computing it. But certainly, if I want to evaluate the factorial, I could do it using this expansion here. So here's an iterative procedure to do that. So it's called factorial iterative, and I'll let you guess why I've decided to clarify that this is the iterative version. So what I do is I just run this loop to multiply every value from 1 through n and then return the result. And as we've seen before, there are times when I design an algorithm and I have to provide a proof of correctness, and I claim this is not one of them. I claim that the correctness of this algorithm should be reasonably clear to anybody familiar with algorithm analysis. If I were really a formalist, I could write a proof, but I would expect you to want to skip over that part of the video anyway, so the proof would go to no use. Similarly, we can talk about the running time of this. So the exercise here is give a big theta expression. It's basically review. I'm just going to go right out there and say, this is big theta of n. There we go, problem solved. And I think that we all know that by now. I think it's clear to us, even if we don't go around counting operations, it's pretty clear this is big theta of n. So thinking back to the same analysis we did with the convex hull algorithms, and even with things like binary search before, it's pretty easy to stare at this and say, okay, well, that's going to be a constant, this one line inside the loop body. All of this stuff outside the loop, well, that's going to be constant as well. So we could write up an expression in the vein of these things, but we could just look at it and say it's going to be constant. So who cares? Really, the only part of this function that depends on n is the number of iterations of the loop. And I guess the loop has what, n minus 1 iterations? But notice how in my original answer, I didn't even think about that. I was like, look, the number of iterations is more or less n. It might be n minus 1, it might be n minus 5, who cares? Because n minus 5 is big theta of n. So I know that the algorithm is big theta of n. And that's what we're working towards. We want to be able to do that. We certainly need to be able to write proofs when the time comes. We need to be able to justify formally the results that we come up with. But for the sake of learning about algorithms and talking about algorithms and exploring the world of algorithms, we just need the ability to know that we all together possess this knowledge and this skill of staring at pseudocode and breaking it down and being able to say how fast it runs, so that later when we talk about complicated problems and different algorithms to solve them, we can glance at them and say, well, this one's n cubed, this one's n squared, and this one is n log n. So that's one of the reasons I wanted to talk about the convex hull algorithms, is to show off that that's sort of our goal. We don't always want to sit around and write tedious proofs. Now in this lecture, I'm going to go and do that. And I've told you at the beginning, don't panic. The reason we're doing this is to lay down a foundation so that later we do not have to do things that are as tedious. Anyway, so at this point, the slides are catching up to us here. It might be easy to observe the algorithm is big theta of n. And we can do this just by basically glancing over it. Now, we could, if we wanted to, say, look, the running time of the algorithm can be characterized by an expression like this, c times n plus d, where c and d are constants. And then, of course, that's big theta of n. And notice that even if I were to do a low-level analysis, I might work out, okay, so this is, what is this, like 1 or 2 operations here, and the loop is 1 operation. So each iteration is something like 2 operations, and there are n minus 1 iterations of the loop. And then I've got, 2 operations here, or something like that. The issue is that ultimately that's still going to work out to just be something like this, a constant times n plus d, and that's going to be big theta of n. So we don't need this expression, although if we ever encounter an algorithm that's a bit weird, so if we ever run into some pseudocode that doesn't look like anything we've seen before, using an expression like this might be quite helpful. Working it out all the way through would be a nice way to make sure that we're doing the right thing, to reassure ourselves. We don't want to jump to conclusions if we're working in unfamiliar territory. So we have this operation counting methodology just in case we need it. We keep it in our back pocket. Speaking of which, let's take a look at this. Here is a recursive factorial function. And we want to we've been given this as a task, it's not just an exercise, we have to do it now, give a big theta expression for the worst case running time of this thing. All right, so speaking of being in unfamiliar settings, what do we do about this? So it's hard to tell, and we can see that, this doesn't actually, there's some sort of unintuitive things going on here. And there are some intuitive things. We can stare at this and say, wait a minute, we're computing a factorial. Well, the last time we computed a factorial, it took n operations. And it seems weird that it would require constant time. So it sort of seems like it ought to require n operations. And actually, a hint is that we're computing the factorial by multiplying things. If we glance over this, now one of the reasons I chose factorial was because it's very likely you saw factorial as one of the introductory examples of recursion back in first year programming. The other introductory example you might have seen, although maybe not from me, is the Fibonacci numbers, and I do not want to talk about computing those recursively right now. I'll come back to that. I've got a few things to say about that, but I don't want to deal with it today. So because you've seen recursive factorial before, you could probably glance at this and say, this does appear to be a recursive factorial function that computes the factorial by multiplying n by n minus 1, or actually, in general, what it does is it does a recursive decomposition. It says n factorial is equal to n times this thing, n minus 1 factorial. And that's a good recursive decomposition. And then the base case is that 1 factorial equals 1. And so this is clearly computing factorial by multiplying a bunch of things together. And if I look at the expansion of n factorial with multiplication, it pretty clearly requires more or less n multiplications. And so it seems like I ought to be able to say that this algorithm is big theta of n or something. Maybe it takes longer. Who knows? Maybe the recursion makes it take longer. So that part is intuitive. What isn't so intuitive is that my analysis techniques that often rely on stuff like staring at the code and saying, there's the loop, and the loop runs for n iterations, they don't really work here because there is no loop. I mean, there's something that sort of resembles a loop because recursion has certain similarities to a loop, but this isn't a loop. So what do we do? Well, how about this? You know, if you can't get the answer right, you can always go for part marks, right? So we know that this is not constant time, but maybe we don't yet want to claim that it's linear. We don't want to claim that it's log n or n squared or anything. So what can we do? Well, I guess I could say, look, I don't know what to do with line 6, but I want some part marks. So let's come up with an expression for the running time, t of n. And I'll just break it into cases. Okay, so there's this stuff. If n ends up equaling 1, okay, well that's easy. So if n equals 1, I do one comparison, and I think I will just do full operation counting because this is such a weird setting that I don't want to make any mistakes. So I'm going to do the full low-level operation counting. If n equals 1, okay, well that's one operation, and then return, that's one other operation. So if n equals 1, then I do 2 operations. So t of n equals 2. Okay, but then what happens with this recursive case? So I can try my best to figure out what to do with this recursive case. So you give me a value n, and it's not equal to 1. Well, it doesn't matter whether it's equal to 1 or not. I still have to do this comparison. Okay, so let's count the operations we need here. So there's one operation needed for this comparison in the recursive case. And then if n is not equal to 1, I get down to line 6. On line 6, what do I do? Okay, I do the recursive call. I don't know what to do with that, but I do a few other things that I can count. I do a subtraction, okay, that's one operation. I do this multiplication, okay, that's one more operation, there's 2. And then I do a return statement, that's 3 operations. Okay, so I guess I could hypothesize that in the recursive case, so that would be in the case where n is not equal to 1, although I should add for simplicity, I'm assuming we're not trying to compute negative factorials here, and as I said, I don't want to argue about what that means, so just come to the office hours if you want to think about negative factorials. I'm going to assume that we only work with n greater than or equal to 1 here. So if n is greater than 1, I guess I need 4 operations plus whatever the time required for this recursive call is. But then I think, you know, if only it were the case that I had a function that told me how long the factorial function took. And you know, I do. It's this, t of n. So I suppose that means it takes 4 times t of n minus 1, 4 plus t of n minus 1 operations. So I have this expression for running time, and my expression itself for the running time, my expression is recursive. Okay, but that's a start. I mean, right? So basically, I can break it into cases. I can say, look, when n equals 1, that's one thing. I can just do operation counting. And as I said, I'm doing operation counting here because it's unfamiliar. I'm scared. I don't know what to do, so I'm going to do the most basic analysis I can. Soon, we'll be able to break this back down into, okay, this part's constant, that part isn't. But for now, we'll do the full operation counts. And then, so in the recursive case, I end up down here, and as I said, we need t of n minus 1 operations for the recursive call, and then I have to count up 4 others. So the if statement condition, the return statement, the multiplication, and the subtraction. And so the expression I end up with, if we go back a few slides, that's this thing, and if we typeset that nicely, it ends up looking like this. And this, because this formulation of t involves a recursive call, we're going to call this thing a recurrence relation. Now, just to sort of put a bookmark here for later, we don't know necessarily that there might not be another way of writing the function t that doesn't involve a recursive call. I mean, there are cases where you can write, I mean, as we know, I could define factorial. So let's say I define the function f of n equals n factorial. And there are lots of ways I could express that function. I could say f of n equals, and you could think of this as sort of the iterative representation, the product of I as I goes from 1 up to n. That's one perfectly valid way of expressing the function f, in this case, capital F. Or I could write something like this. F of n equals 1 if n equals 1, and it equals n times f of n minus 1 if n is greater than 1. Now, this is just another way of writing the algorithm I've written on the left, but notice how both of these are the same. F of n is actually the same in both cases for all the things in the domain that I care about, so for every integer greater than or equal to 1. There's no reason why t of n doesn't have the same property, so for all I know, there might be a way of writing t of n that isn't as difficult to work with as this, but I don't have it. I only have this form, and this is the form I derived directly from my algorithm. As I mentioned, we'll talk about techniques to try and wrangle these things in the next lecture. I'm going to talk about one of them today, just to sort of set the stage for that, but we'll see in the next lecture there are some things we can do to recurrence relations that make them easier for us to work with. And also keep in mind that just because I have chosen to express t as a recurrence relation doesn't mean there isn't some simpler form out there. And we'll see in the next lecture that if I can discover that simpler form and prove that it works, then I can just analyze that instead. So I have this recurrence relation for my running time. And of course, now the question is, when I have this recurrence relation, how do I use it to achieve some big theta? So how do I turn it into a big theta expression? Not only how do I prove that it's big theta of something, so I mean, suppose this turns out to be big theta of n squared. How do I prove that? But actually, before that, a much bigger existential concern is, how do I even know what to do with it? Like, is it n? Is it n squared? Like, what do I do with an expression that looks like this? How do I even guess, frankly? Well, one option, I guess, is to try looking at values of t. Now remember that writing out values of t proves absolutely nothing. I'm doing this only to try and get some mental picture of what's going on. So of course, if I write this out and say, hey, it looks a lot like t is greater than n, well, yeah, I think so, but I can't prove that until I've written a proof. You can't just stare at a table of a few values and draw and jump to conclusions. It proves nothing. For all we know, as of n equals 7, t starts equaling 0 forever. I hope not, but maybe that's the case. We need to write a proof. So my observation is based on looking at the value of t, and I will add a sort of suspicion that I have that this is probably going to be linear because the iterative version was, and that can inform my thinking, but it's just a suspicion. So based on looking at the values of t, I stare at it for a while and I notice that t seems to be going up in steps of 4, and that makes sense because in the recurrence I keep adding 4 at each step recursively. So t goes up in steps of 4, and at each step, t is greater than n. So t of 1 is greater than n, t of 2 is greater than 2, t of 3 is greater than 3, okay? And that similarly, this is each value is less than or equal to n times 4. So this is 2 times 4, so 8, 12, and then this is 1 times 4, which is 4. So I notice that t of n does seem to be sandwiched between n and 4n. That's my observation. I haven't proven that, but I could try and prove it now. I could use this as the basis of a guess, I guess. I could say, I think t of n is linear. Because, of course, if I were able to prove this fact, that would be enough to say that t is big theta of n. Because what I'm showing is n is big O of t and t is big O of 4n. And that means that they're all big theta of each other. So I could, based on this observation, try and write a proof of this. Okay, I could just go ahead and prove it. Now, how do you think I might want to do that? Well, let's see. I could write an induction proof. And one of the reasons we love induction so much in this course is because induction and recursion are basically the same thing, if you think about it. Recursion is a computational version of induction in some sense. And so it doesn't surprise us too much that we often can use induction to prove things formally about recursive algorithms. We can use induction for all sorts of other stuff too, of course, but it's very helpful for this. So what I'll do is I'll just break this observation into two pieces. So really I'm saying two separate things here. I'm saying n is less than or equal to t of n, and t of n is less than or equal to 4n. And so I'll just write proofs of both of these. And if you notice that this results in very verbose, like lots of proofs being written, yep, that's exactly the point of this example. I'm trying to show this is sort of tedious, and I find it tedious too. So don't panic, we're going to find some easier ways of wrangling these things later. All right, so the first claim I want to prove is that n is less than or equal to t of n. Now, I'm going to admit that this is a weird order for the inequality. I'm doing it this way deliberately because I want to have it be identical to the thing that I was saying on a couple of slides ago. But to be honest, I would really much rather prove this. I know it's the same algebraically, but to me it always seems weird to have t of n appear on the right-hand side. So I actually may stumble through explaining this because of how strange it is that I've written it in this order. But for some reason, I'm committed to doing it that way because I want the inequality to appear in the same order as in my guess. All right, so the proof is by induction. When I look at n equals 1, that'll be my base case. I notice that when n equals 1, 1, which is equal to n, is less than 2, which is equal to t of n. So we're good. The claim holds. Okay. Induction hypothesis. Suppose the claim holds for some n greater than or equal to 1. And notice that the hypothesis covers the basis case with the value of n. Okay, induction step. Consider n plus 1. Okay, well, the very first thing I do is I say, well, let's look at t of n plus 1. So based on the recurrence, if I assume that n is greater than or equal to 1, then n plus 1 has to be greater than 1, which means that I have to use the recursive form of the recurrence, so the recursive case. And that means that by the definition of the recurrence, t of n plus 1 would be 4 plus t of n. That's literally what this says if you apply it to n plus 1. By the induction hypothesis, so we know that n is less than or equal to t of n, that's the induction hypothesis, for some value of n, for the value of n that we're working with here. So that means that t of n is greater than or equal to n, which means that t of n plus 1 is greater than or equal to n plus 4. So what I've done there is I've said t of n plus 1 is equal to 4 plus t of n. And because I know that this is greater than or equal to 4n, this is greater than or equal to n. We're not at the 4 case yet. That means that I can just plug n in here and then add an inequality. So that'd be 4 plus n. And I notice that 4 plus n is definitely greater than or equal to 1 plus n. That's a pretty easy one. And that's obviously equal to, just flip those around, that's equal to n plus 1. And so I've proven what I want to prove. The claim applied to t of n plus 1 is the claim that t of n plus 1 is greater than or equal to n plus 1. So that actually might be more writing than we need for this. Maybe it was sort of obvious from what I already had there. But in any event, I am able with a series of pretty simple inequalities to show that the claim holds for n plus 1. And therefore, by induction, that the claim holds for all n greater than or equal to 1. Okay, good. I'm halfway there. I've proven that t of n is big omega of n. Okay, now the other half of the proof. T of n is less than or equal to 4 times n. Okay, so it's also by induction. And we basically, notice how I'm pretty much filling in the blanks here. This is the same proof, just with a couple of things, a couple of equations swapped out. Okay, so when n equals 1, t of n is 2, and that's by definition. We can just say that. I don't need to prove that any further. And of course, 2 is less than 4, and 4 is equal to 4 times n, so the claim holds good. A hypothesis is literally, I literally copied and pasted the hypothesis. And then consider n plus 1. All right, so again, by the definition of the recurrence, t of n plus 1 is just equal to 4 plus t of n. And I will point out, if you write a proof about a recurrence, you don't actually have to say this is by the definition of the recurrence in a case as simple as this, when you're just plugging a number into t. That's fine. You can just use it. But I'm doing it because it's the first one of these proofs that we've seen. By the induction hypothesis, t of n is less than or equal to 4n, which means that if I just follow that through, if I plug the hypothesis in, so t of n plus 1 is equal to 4 plus t of n, and that means that by the hypothesis it's less than or equal to 4 plus 4n, and then of course that's just equal to, well, that's 4n plus 4, and then that's 4 of n plus 1, which is exactly what we want to show. And so the claim holds for n plus 1. So we've shown that t of n plus 1 is less than or equal to 4 times n plus 1, and the combination of the 3 steps mean that, therefore, by induction, the claim holds for all n greater than or equal to 1. Okay, so I just had to write 2 induction proofs that were perfunctory. I mean, frankly, very little interesting stuff actually happened in these proofs. I did this bit. I guess that was useful, but even that wasn't that exciting. But I had a lot of work to do just to set up the infrastructure to prove this relatively basic fact about a relatively basic algorithm. And so now we can say, finally, that because this, n less than or equal to t of n less than or equal to 4n, so because it's the case that whenever you can prove a real inequality, like the real less than or equal to operator, you automatically get the asymptotic version. So if I know that n is less than or equal to t of n, I automatically get, so this is true for all n greater than something, so in this case greater than or equal to 1. If I know this, if I know the real inequality, then for free, I can assert big O, because big O is a weaker condition than the regular inequality operators. Okay, and then similarly, I've also shown that t of n is big O of 4n, and because n in for n are big theta of each other, that squeezes t of n to be big theta of both. And so t of n is big theta of n. Okay, great. So we just spent, as I said, like 10 minutes writing these proofs. The proofs were nice, they were well formatted, and they were clear, but that's a lot of writing just to establish a basic result about a simple algorithm. This is what? Like, how many lines of real code appear here? I'd say, like, we don't count the else and the and if. I mean, there are pretty much 3 lines of essentially trivial code in this algorithm, and it took us this long to prove that it was big theta of n. I guess it's true that I have now spent maybe 5 minutes complaining about that, so that might have accounted for some of the time. One thing to observe is I had to go and do full operation counting there because I was uneasy about the situation. But actually, on any architecture we're familiar with, anything fitting the random access model, we can expect that the recurrence we came up with for the factorial function would be this. It would be some constant in the base case. We don't know if it's the same constant in the base case and the recursive case. And then some other constant in the recursive case plus t of n minus 1. What we'll notice later is that the most salient details of a recurrence of this form tend to be basically, we don't care about the constant. That could be 1, that could be 5. It is important whether it's 1 or 0, though. So if there's no constant here, that does make a difference, although that's very unusual. Like, think about how an algorithm could exist that didn't require any operations besides the recursive call. That doesn't make very much sense. It would have to be a very trivial algorithm. The other salient detail is the recursive call multiplied by anything? So basically how many recursive calls were there? This recurrence is pretty much going to be big theta of n no matter what the constants are. However, if I add a constant multiplier to t, something changes. And it's interesting, if you were to, as an exercise, just try that out. See what happens if you multiply t by 2. Actually, you could do it for our recurrence from earlier. If you do it for this one, see what happens if I do 4 plus 2 times t of n minus 1. Definitely we don't end up with the same, we can't prove the running time the same way. The running time will look quite a bit different. So basically what I'm saying here is that we can do the same generalization we do with iterative algorithms. We don't actually have to count operations. It's sufficient to just say, look, the base case is constant. The recursive case requires a constant amount of work plus 1 recursive call, and the recursive call is on n minus 1. We do care that, and that's the third salient detail, we do care that the recursive call is on n minus 1 versus, let's say, n minus 5, although that would be sort of weird, or especially things like n divided by 2, because if we cut n in half, we can expect the algorithm will have quite a bit different of a running time than if we have n minus 1. So therefore, pretty much, we can do the same thing we've done before. We just argue that a particular part of the algorithm is constant, and we just boil it down to the most important details, which tend to be how many recursive calls, how much work is a function of n, how much constant work, and just give the constants, have these unknown constants show up in your recurrence. It's also possible in many cases, we're not going to follow up on this statement too much, it's just there so that we can keep it in mind for later. But in many cases, because counting operations, every single operation can be a huge pain, it's usually fine if we can justify this to only count certain operations, as long as we can argue that those operations are an effective proxy for all of the operations. So just to sort of foreshadow this, I don't want to go into more detail about this now, but just to explain what I mean by that. So notice how in this algorithm, no matter which path of control I follow, I hit a return statement. Notice also that the amount of work that I do is constant. Like if I do one return statement, I might do 5 other operations, but I don't do n other operations. I do a recursive call, and then there are return statements. So what I actually could do here is I could analyze the algorithm by just counting return statements and recursive calls, and argue that every time anything else happens, it happens before or near a return statement. So I could just use return statements as a proxy for all operations. And that's valid, and we'll see it happen a few times, and when we get to a case where it applies to a real algorithm, I'll reason about it further. But that can be helpful to avoid having to nickel and dime your operations. Like having to make, if we do full operation counting, what if we miss something? Like, what if I miss that subtraction? Well, it makes no real difference because it's just one fewer operation. As long as I'm counting in general that there's at least one operation happening in this block of code plus the recursive call, I'm going to get the right answer big theta-wise at least eventually anyway. Okay, so there's that. And so what we've seen already is even for a basic algorithm, analyzing it recursively can be a bit of a pain, although we can do it. So what I will point out is one way or another, we actually did prove that my recursive algorithm was big theta of n. So we have already the tools that we need to do this. We have induction proofs, we have the ability to design recurrence relations. Let's go back to binary search. So here's our sorted array search problem from a few lectures ago. So it's the version of searching where we can be guaranteed the array is sorted. And here is our iterative binary search algorithm. We already saw this, and we wrote a proof, not only that this was correct, but also that it does have log n performance. And I didn't like that there were some aspects of the proof that we wrote that I wasn't fond of at the time, so I was missing a line of algebra somewhere that I had to write in by hand. I'm actually going to prove it again here, but I'm going to prove it for the recursive version. So if you thought I had no idea what I was doing back 2 lectures ago, don't worry, I'll make up for it now, or I'll make the problem worse, I guess. I'm going to analyze essentially the same algorithm again, but through a recursive framework. I'm not going to worry about the iterative binary search algorithm again. That's actually a few too many lines of code for my taste. So here is a recursive binary search algorithm. I had to set up a couple of details before we can go any further. So because it's recursive, it calls itself, and that means that we have to quantify, if I want to analyze it and say, I suppose my suspicion is that recursive binary search is also log n. Now, that's a suspicion that I have because I have the luxury of having analyzed the iterative version. But what's n? Where do I use n here? And obviously we could claim that the size of A is equal to n, but that might be missing the point a little bit. So that's one thing we have to think about. Another thing we have to do, like the first thing we have to do when we show recursive pseudocode, is explain how would you call this the first time. Like, we can see that binary search calls itself, but if you want to use binary search, what's the initial call? So typically in these lectures, what I'll do for that is I'll show the recursive code, and unless the initial call requires some kind of setup, like unless it requires a bunch of initialization or something, typically what I'll do is I'll tell you, if you want to call this to do a search, here's the call you would make. Here's your initial call. So in this case, we can do that. So when you want to search for a value k in your array A, you just pass in 0 and n minus 1 as the other 2 parameters. And those become the range low and high. And remember that our analysis of binary search basically depends on this idea that we have this range that we're keeping as the possible set of indices that could contain the value that we're searching for. And then we narrow that down. We sort of cut that range in half, more or less, at each step. And you'll see that the process of cutting it in half is really annoying to analyze because we have these ceiling functions and floor functions. That's going to come up here as well. Anyway, so what we assume is probably happening here, because we know about binary search already, is that every time I make a recursive call, the range that the recursive call works with is about half as big as the range that I started with. And we're going to use that observation to sort of conclude that if we want to analyze this in terms of n, some parameter n should probably be the range at each step. Or moreover, if I want to say this call here is big theta of log base 2 of n, really the n I'm talking about there is the size of this range, the size of the range of the call in the call that you made. And at every step we can think of the range at this point is some value n that's just the difference between low and high plus 1. So the first question is, can we derive a recurrence for this, for the worst case running time of this binary search function? So as I said, at each step, like for one call to this function, if we think of the value of n, we should, so if I wanted to, write a recurrence t of n to refer to somehow encapsulate the running time of this recursive call, so one particular call to this function, I have to define n, and I'm going to argue that the input size n at each step, so n is a stand-in for input size, is just this. It's the number of indices left. And I like that because it does allow us to map n pretty conveniently onto our base case, because we know that eventually the size of the range will be 1, and then there are no indices. There's only one index left to check. And unlike in the scale problem that we analyzed pretty exhaustively a couple of lectures ago, we know that the array-based binary search problem, when there's only one index left, if I manage to narrow down the possible parts of my array, if I'm looking for a value k, and I narrow it down to one index, well, it could be that I go looking in there and I don't have the value k. So of course I still have to check that index. But overall, the goal of binary search is to narrow down the range of indices until there's only one index left. Now let's take a look at the base case. So this covers the situation where I've only got one index left and I have to check whether it contains the element that I want. I've actually built in a bit of safety here just in case. So suppose we end up doing a recursive call where low equals high, or where low is less than high or something, just to avoid any weird issue with recursion happening there. I'll just say, look, how do we do this? If low equals high, go look at that index of the array. If it equals k, then we're good. Return the index of low. Otherwise, if low is greater than or equal to high, just return -1. The element was not found, so we're good. good. Don't worry about the degenerate case where low is greater than high, basically. That's the base case. And I can argue, and again, like I said earlier, we I think have seen by now, we've seen enough to sort of recognize that we don't need to do full operation counting for this. And so I can argue that this entire thing takes some constant number of operations, this entire base case. So as I said, I put this in here deliberately because I want to make it absolutely clear that as soon as the range has size 1 or less, even though really it'll never have size less than 1, there's no way that when the range has size 1 or less, it will ever take any more than this number of operations because the function will be over by line 6. Okay, so that means this entire base case block at the beginning requires some constant number. Who cares what it is? We'll just call it C sub b. Okay, that's our base case. And so we can begin drawing up our recurrence. So T of n, and remember n is our input size, it is equal to this if n equals 1. And then the question is, what's the recursive case? So we'll work on that next. Okay, so in the worst case, and remember we're doing worst case analysis here, we're talking about the big theta for the worst case running time. In the worst case, the algorithm, unless it hits the base case, always makes a recursive call. Because notice line 14, I mean, maybe you could argue line 14 is a sort of extension of the base case. So what if it happens that the index you look at, so I look at index I of my array, if I look at index I, maybe I'm lucky and that's the thing I'm looking for. But of course, we're doing worst case analysis, so let's assume I'm not lucky. That's what this is saying. In the worst case, we do not return on line 14. We go all the way down. We just narrow the range down over and over until it has size 1. We do not happen to be lucky in the meantime and return early. So in the worst case, we always make one recursive call, not two, just one, and it happens whenever n is greater than 1. And so reaching the recursive call requires a constant number of operations in both cases. So we don't want to count them individually, that's a huge pain, but notice that, okay, I need some operations for this, I have to do this comparison, and then maybe I do this recursive call. If not, I do this other comparison and then this recursive call. And you can see that I guess I require a few more. If I require like Q operations here, I probably require, I don't know, like Q plus T operations to get all the way down here because I have to do this extra comparison or something. But who cares? We know that in the worst case, the number of operations for either required before either recursive call is, let's say, at most this number, some constant, CR. And because we know by now that the actual number of operations is sort of irrelevant if it's 5 or 7 or something, and that adding or subtracting 1 or 2 from that doesn't really change anything. So total number of operations excluding the recursive call is, let's just say, some number CR, some unknown constant. And then there's this. Okay, so this is, as I said, we're going to have some tedious stuff to worry about here. To set the stage for that, let's work out what we have so far. Okay, so T of n equals what? Okay, well in the base case, when n equals 1, so that's if n equals 1, it's equal to C sub b, the constant number in the base case. If n is greater than 1, let's move this over. If n is greater than 1, then what? Well, it's going to be C sub r plus the recursive call. Okay, but what's the size for the recursive call? Is it n minus 1? Probably not, because we expect that we're going to be dividing the range, and n is referring to the range size. We expect we're going to be dividing that by 2. Is it n over 2? Well, not quite, because what if n is 7? Well, n over 2 is 3.5. That's not a valid size of a range of indices. So we've got to deal with this really annoying problem of truncating a number or rounding it, I guess, to an integer. Okay, I'll spoil this. We'll spend some time circling around this issue in the next lecture, but basically in this course, it turns out that we can just say n over 2 and treat the recurrence sort of like a real valued function, and we get a result that's big theta of what we want, unless we're working with incredibly strange algorithms. So as long as we're working in the hierarchy of, let's say, n or n squared or n log n, we'll be fine if we just say n over 2. But we're not there yet. We need to see the inner workings of this mechanism, and we therefore have to treat this thing as if we're not allowed to make that assumption. Okay, so what I have to show pretty much is that the size of the range for both of these different possible recursive calls is more or less n over 2. It's half of the range I started with. And you'll recall I had to do this algebra, the iterative version of the same algebra, a couple of lectures ago, and that's where I had a couple of algebraic mishaps where I had a few steps that I had to write in by hand. So what I've done here to try and simplify that, because I felt like even then those steps were a little bit convoluted, I've used a little bit of a different technique here. Maybe, so if you didn't like those ones, try looking at this. You could actually use this logic for the iterative version of the proof as well, where it really amounts to how do I get rid of the floor function. All right, so what I want to show pretty much is in both cases, for both of these recursive calls, the range ends up being more or less half of what it was before, hopefully less than half. So recall that the size of the range is this number. It's high minus low all plus 1. Okay, where's the plus 1 come from? Well, suppose the range is 5 through 7. Well, then it contains 5, 6, and 7. And if I just do 7 minus 5, that's 2. So I have to do 7 minus 5 plus 1 to accommodate that it's an inclusive range. The endpoints are included. So if high minus low plus 1 is the initial size of the range, then in the recursive call, the range will be one of these two things. So in the event where where I minus 1 becomes my new upper bound, so when I do this recursive call here, then the new range will be this. So this thing here, I minus 1, becomes my new high. Okay, so we'll just do the algebra there. So that ends up being, so there's I, so that ends up being this thing minus low. Okay, so right off the bat, I can cancel out this minus 1 with this plus 1. And then I end up with this, high plus low all over 2 minus low. Okay, what do I do? And this floor function is just such a pain. Okay, here's what we'll do. We're going to put low and high, low and the term for I on a sort of common denominator. We'll start with that. Okay, and then I'm going to observe that the floor of 2 times low over 2 is just going to be equal to low. That is, because the thing on the top is even, there's not going to be any fractional components, so therefore the floor isn't actually necessary. And I'm going to argue based on that because I'm adding 2 times something here, it actually is pretty easy to bring the entire thing inside the floor function. Now, just to be clear, in general, it is not true that floor of x plus floor of y equals floor of x plus y. That is not generally true. Do not claim that in general. I'm arguing that here based on a special pleading, based on the case that this thing is actually not going to have a fractional component. In other words, it is true that if I say something like the floor of 3.5 plus the floor of 3 is equal to the floor of 6.5. And my argument for that is simply that because the thing I'm adding doesn't have a 0.5, it doesn't have any fractional component, there's no way that it affects the, truncation behavior of the floor function on the left. That is the argument I'm making. Oh, okay. So anyway, what I'm saying there is it's reasonable to say, hi, I got so worked up that I deleted the algebra I was writing, minus low over 2 times low over 2, that in this case, because this thing, 2 times low over 2 is an integer, it's reasonable to drag it inside the floor function with no adverse consequences. And then finally, what I do, if I just cancel out the plus low over 2 minus 2 low over 2, I can reduce the whole thing down to this. Okay, I hope that was a good enough explanation, but if you want a better one, come to the office hours, although I have no idea what else I could tell you. Okay, so anyway, that's less than this. And of course, notice how high minus low is equal to n minus 1. Okay, so what I showed was in this recursive call, the size of the range is at most, via that less than or equal to sign, the floor of n minus 1 over 2, which of course is less than or equal to n minus 1 over 2, and less than or equal to n over 2. Okay, there's that. What about the case where I have my new lower bound is I plus 1? Okay, well then my new range is high minus I plus 1, all plus 1. Okay, so again, I can cancel out this plus 1 actually is a negative 1. So I can cancel that with this. And then the question is, okay, so I've got high minus high plus low over 2. And what's that equal to? Well, I could try and reason about that semantically, but I'm going to leverage this property here, which is that and this only works for when I divide by 2. The floor of n over 2 plus the ceiling of n over 2 equals n. That's true whenever we divide by 2. It's not true when we divide by other things necessarily. I'm not claiming it is. I'm saying it's only true when we divide by 2. And if I fiddle around with the algebra there, what I end up saying is something like n minus the floor is equal to the ceiling. So I'm just rearranging terms. And I mean, astute viewers will note that this is not high and high plus low over 2 are not the same thing. But via some algebraic manipulation, hopefully it's clear that I can end up with saying something like this. High minus low over 2. The ceiling, though, of high minus low over 2, just by fiddling with terms. And so it's really annoying to me that I have a ceiling on one end and a floor on the other. That actually really makes my life harder. We'll see that it all works out, although it makes my eventual induction proof even more unpleasant, but bear with me. So what I've shown here, and there's maybe more tedious algebra you might need to justify this, but try it out yourself. You'll probably discover that everything works out if you work through the algebra line by line. Anyway, what I've shown here is that in either case, for either recursive call, the size of the range is at most, okay, which of these two things is larger? It's going to be that one. It's at most this. It's the ceiling of n minus 1 over 2. Okay, so one observation that will make our lives so much easier later in the course is that the ceiling of n minus 1 over 2 has to be less than n over 2. And therefore that if I could just use n over 2 and get rid of the ceiling, everything gets so much easier. I don't know that yet, so I'm just going to keep going with the ceiling. So what we've observed is the range in my recursive call is at most this thing. All right, so in either recursive case, the range provided for the recursive call has size at most this. And that means that our recurrence finally ends up being this. T of n equals C sub b in the base case. And I've even written the base case as n less than or equal to 1, just in case there's a situation where the range comes back having size 0. And then in the recursive case, it's C sub r plus T of the ceiling of n minus 1 over 2. Okay? So what do I do with this? I have this. Is it like it's not clear what asymptotically t is supposed to be? Is it n? Is it n squared? It's not obvious. So basically what we can do is try and guess. And this is really weird. This is creepy because we can guess, frankly, because we know about binary search. But the point of learning to analyze algorithms is that we're going to learn about algorithms we've never heard of. We're going to invent brand new algorithms that might be completely novel. So how can I assume that I can analyze algorithms if I have to already know about the iterative version? There are plenty of algorithms where the iterative version is so hideously complicated that it's very hard to analyze to begin with. So in this case, because I know that iterative binary search is log n, I could sort of guess maybe T of n is also, whoops, that's a typo, also log n. And then try and write proofs based on that. But I want to make it really clear, it's not obvious how to guess this methodically. I'm just benefiting here from the fact that I already know about binary search. It's also not clear exactly how I might prove the guess to be correct. I mean, I know I can use induction to prove it, but what specific formula, like what multiple of log n or whatever do I use? Okay, so I could just try and evaluate T of n. Now, I can't evaluate to a number because I don't actually, have numerical values for CB and CR, but I could write out expansions of T of n symbolically for a few values of T to help form a hypothesis. And I would argue, so here's the value of T from 0 up to 17. And I don't think there's any obvious pattern here. I mean, yes, I do see that the coefficient of CR seems to keep going up. I don't think I would have to stare at this for quite a while before I notice any pattern, so I don't think it's obvious. So don't feel bad if you don't notice an obvious pattern either. In the interest of keeping things going, I will spoil where I think the pattern ends up being, and because I sort of already know to look for log n, it informs where I go looking for this pattern. What I notice is, if I look at powers of 2, and the reason I like powers of 2 is that log n base 2 is easier to evaluate for them. So I notice that 2 to the 3 equals 8, and notice how when I have 8, I get a 3 in front of CR. When I have 4, I get a 2 in front of CR. Log base 2 of 4 is 2. When I look at 16, I get a 4 in front of CR. And so I begin to, and of course, obviously log base 2 of 15 is definitely less than log base 2 of 16. And because log base 2 of 16 is 4, and because also log base 2 of 8 is 3, I would expect that log base 2 of 15 is 3 point something. So it does make sense that if I have a 3 here, what I'm sort of saying is that maybe the pattern I'm looking for is that T of n is less than or equal to CR times log base 2 of n. It doesn't matter that log base 2 of n could be some fractional value because I'm saying less than or equal to. And again, assuming that log base 2 of 15 is 3 point something, well, 3 times CR is less than 3 point something times CR. So let's try proving that. So let's try and prove that t of n is less than or equal to c sub r times log base 2 of n plus c sub b. Okay, now we already have a problem on our hands, which is that the recurrence does have a value for t equals 0. I mean, it's just CB. I'm allowed to evaluate it. But this claim doesn't apply for n equals 0. I can't use n equals 0 because if I were to claim that t of n is less than or equal to cr times log base 2 of 0, that would put me in a difficult situation. So I can't do that. So what I have to do is just start my induction proof one step higher. I'm allowed to do that though, because for asymptotic proofs, all I have to show is that t of n is, let's say, big theta of n or big theta of log n. That only requires that I show it for large values of n, so I can ignore n equals 0. But notice that just like to add insult to injury, we also have to worry about n equals 0 not being defined. Okay, so my base case has to be basically n equals 1, or maybe n equals 2. Now, there's an issue here, which is that because I'm working with this recursive call that divides by 2, I have to make sure that any recursive call I do doesn't end up depending on 0, because I do not want to work with I don't want to ever have to state my claim for n equals 0, because I can't, it doesn't apply to n equals 0. So here's what I'm going to do. I'm going to have a basis with n equals 1 and n equals 2. And my logic there basically works like this. So t sub 3, or t of 3 is equal to cr plus what? Plus t of, okay, so 3 minus 1 over 2. Okay, that's t of 1, right? Because 3 minus 1 is 2, and so this would be 1. Okay, so t sub 1. So it looks like basically every term after t3 will depend on t1 or t2 or t3 or t4. Nothing depends on t0. On the other hand, if I look at t2, t2 equals cr plus what? Well, the ceiling of t of 2 minus 1 all over 2. Actually, you know, that might work as well. Okay, so 2 minus 1 over 2, let's see, so that's equal to CR, sorry for writing up in the margin here, plus, okay, 2 minus 1 is 1, that divided by 2 is 1/2, that's going to be t of 1. So actually, t of 2 doesn't depend on 0 either. But to play it safe, we'll just put both n equals 1 and n equals 2 in our bases, just to leave this, so we don't have to worry about it anymore. Okay, when n equals 1, t of n equals CB by itself, because that is the base case written into the recurrence. And log base 2 of 1 is 0. So of course I can always add this term gratuitously. And so the claim holds because CB actually equals log base 2 of CR times log base 2 of 1 plus CB, since that ends up being 0. Okay, so the claim holds for 1. When n equals 2, t of 2 is CR plus T1. Okay, I didn't need to write T2 up above. And then that's equal to, so CR times log base 2 of 2. Well, log base 2 of 2 is just equal to 1, so CR plus CB. And it turns out that the claim holds there as well. Because t of, I guess I omitted a step, but t of 1 is CB. So this ends up just equaling CR plus CB, and the claim holds, okay, great, my basis is good. And I'm already running out of patience for this proof, even though I'm less than halfway through it. Okay, so now I have to finish off the proof. I have to state a hypothesis and my induction step. I have a basis that goes up to n equals 2. And so my hypothesis is, and you'll notice it's a stronger hypothesis. And the reason it has to be a stronger hypothesis is, again, because I'm not just depending on n minus 1. I'm depending on n minus 1 over 2. And even worse, I'm depending on the ceiling of that, whatever that is. I have to be very careful. So I'll state a strong hypothesis so that I know when I work with the induction step that every value of t that I might need is usable, that I'm allowed to depend on the hypothesis for that. So suppose that the claim holds for every value of n from 1 up to k for some value k. And notice that the value of k is greater than or equal to 2, so it does include my basis. It includes at least one element of my basis. And because it's a strong hypothesis, it's actually stating, if k equals 2, that the claim holds for 1 and 2. So both of my base cases do get included in this hypothesis. Now, induction step. Consider k plus 1. So I want to extend this range by 1. Now, I will observe that actually later in the course, we'll often use induction proofs that consider 2 times k if we have to divide by 2, and that's completely valid. In this case, I can do k plus 1. I don't know that it's any easier or harder either way, because if I did 2 times k, I'd spend more time justifying it. Because k is greater than or equal to 2, and this is one of the reasons I had a basis that was so big, because k is greater than or equal to 2, based on my hypothesis, k divided by 2 has to be greater than or equal to 1. So there's no way I'm going to hit 0 in some way here. Now, Okay, I've got this ceiling function, and that's going to be an enormous pain. So to handle it, I'm going to observe basically this. So if a number, let's use q for this. If q is even, then the ceiling of q over 2 just equals q over 2, because q is actually divisible by 2. If q is odd, then the ceiling of q over 2, well, that's going to actually equal, let's see, so if we look at an example here, the ceiling of 7 over 2 is 4. It actually equals q plus 1 all over 2, which again doesn't need a ceiling, because if q is odd, then q plus 1 is even. So what I observe here is that if I break up my induction step into two cases, I can get rid of the ceiling function in both cases. So to handle it, I'll just consider the case, I'm considering k plus 1. I'm going to consider the case where k plus 1 is odd and the case where k plus 1 is even separately. That way I have some way out of that ceiling function. All right, so if k plus 1 is odd, well, that means k is even, obviously. So then t of k plus 1 expands to this thing. So t of k plus 1 would be CR plus t of the ceiling of k plus 1 minus 1. Well, I mean, it's this. K plus 1 all minus 1 over 2. And you can satisfy yourself that that does, in fact, equal ceiling of k over 2. And then, because k is even, the ceiling of k over 2 is just equal to k over 2. Okay, good. So I've gotten rid of the ceiling function. Okay, so if k plus 1 is odd, then t of k plus 1 ends up equaling this thing here. Okay, and then I can use my induction hypothesis. And again, this is an integer, so everything still checks out here. And by my induction hypothesis, which is that this holds for every value up to k, and k over 2 has to be no greater than k, by the hypothesis, t of k plus 1 is less than or equal to this. Okay, so I've got, here is the part that I brought in by the hypothesis. And now I'm going to do some annoying algebra. This is especially adding insult to injury, because I'm going to use the law of logarithms in a way that I think is sort of clever, I suppose, but not something like, if this were on an exam and you'd never seen it before, this is a bit of a dirty trick. Although I reserve the right to require you to know the laws of logarithms on exams now that you've seen it. But it's a technique we just sort of pull out of nowhere in this point. So what I do here is I observe that because log base 2 of 2 equals 1. This is not the only way of doing this, by the way. There may be a way that doesn't involve as many logarithm shenanigans. Because log base 2 of 2 equals 1, I can multiply anything I want by log base 2 of 2 if it makes my life easier. And somehow it actually does in this case. So that means that this line here is equal to this. All I do is multiply CR by log 2 of 2. And then I use the law of logarithms to combine. I now have two terms that are CR times log of something. I just factor out the CR and then combine the two logarithms into one expression, and I get this, all plus CB. And then I notice that I can cancel the 2, and I end up with CR times log base 2 of k plus CB. What I'm trying to prove at this step is that t of k plus 1 is less than or equal to CR times log base 2 of k plus 1 plus CB. And actually, I've been handed a pretty easy case. Log base 2 of k is less than or equal to log base 2 of k plus 1. So I can just say, well, that's easy. I'll just relax that constraint a bit. This is less than or equal to the thing I'm looking for. And now, if I follow the inequalities along, I have actually proven that the claim holds for k plus 1. So there's case number 1. Great. Let's do case number 2. Case number 2. If k plus 1 is even, well, that means that k is odd. Okay, and notice that in this case, that means that the ceiling of k over 2 is actually equal to k plus 1 over 2, because k plus 1 is even, so k plus 1 over 2 is an integer. Then, okay, I just do the same chain of algebra as before, but with a couple of twists at the end. So then that means that the recurrence expands to this. The observation I just made allows me to write this instead, and then I apply the induction hypothesis to this number. And I observed earlier that k plus 1 over 2 has to be less than or equal to k. So therefore, the hypothesis does apply to k plus 1 over 2. Okay, so that means that t of k plus 1 is less than or equal to this thing. And I again do basically the same gimmick as before. And so I say, okay, that's equal to CR times log base 2 of 2. And on the next line, I combine all the logs together. So I just factor out the CR and combine them together. I can then cancel out the 2, and there's my log of k plus 1. Okay, so then I've got t of k plus 1 is less than or equal to CR times log of k plus 1 plus CB. In both cases, I was able to show that the claim held for k plus 1, and therefore by induction, the claim holds for every value of n greater than or equal to 1. What have we learned? Okay, That was pretty exhausting. That was a lot of proof. And you know what? It was a lot of proof for not very much payoff. We have to write proofs like this. This is a fact of life. What we want to do over time is to ideally boil down the recurrences we work with into a few common cases so that we can maybe write one meta proof for the common cases. There will still be recurrences that we have to write complicated proofs for. That's a fact of life. But we certainly need some tools to make it easier in cases where we're, for example, doing one recursive call on n over 2. I mean, that's going to happen so much that we break our input in half and do a recursive call. We do not want to have to write this entire exhaustive proof in every case. And you know what? I should also observe that all this is actually shown is that t of n is big O of log n. I never actually showed that t of n was greater than or equal to something times log n. I could do that. It might be a fun exercise if you still have patience for the topic after this whole saga. And if you prove that it was greater than or equal to log n, that would give you big theta. What I wanted to show here was A, that we can do this. This is possible. It's within our means. We have the knowledge, we have the skills needed to do it. It's within our means, but we have better things to do, basically. So even if we accept that, life's tough and we have to do these tedious proofs sometimes, we actually have this other problem lurking in the background. So even if we're willing, even if we just love writing induction proofs and we're willing to do that every single time, we still have this issue, which is how did I come up with log n? I mean, this all started because I was able to somehow guess that t of n was less than or equal to this expression. And once I had that guess, I was able to write the proofs. And maybe I described the process of guessing as, stare at this and just sort of look for a pattern. I hope I made it clear that obviously when I was making up the slides, I actually had to spend a few minutes figuring this out. I actually went back and forth for a while on which function do I want to go with before I settled on this one. I had to write these values out and stare at them and decide whether I really meant it. Showing slides doesn't give away the amount of time that goes into actually doing this derivation. It's not easy. And the only reason I was able to guess was because I already sort of knew it was going to be log n. What if I don't know that? What if I'm working with a bit of pseudocode that's got a weird recursive pattern and I have no idea what it could be? Do I just try every possible thing? Do I try to prove it's n and then n log n and then n log n squared, then n squared log n and then n squared and then n cubed and then n squared times log n cubed? And obviously that's not going to work. So what I need at minimum, even if I love writing long proofs, at minimum I need some method, some strategy that helps me guess what the asymptotic class of a recurrence is so that I can work backwards and find some way of proving that. But frankly, I also need a way of avoiding these proofs. I don't want to have to write long-form induction proofs for every single recurrence I ever see. I need to have that skill, so of course, this is your warning, you need to be able to do that, but we don't want to do it every single time. We want to have that be one of the tools we keep in our back pocket, but be able to do higher level analysis most of the time. So that takes us to our break between lectures. In the next lecture, I'm pretty much just going to talk about recurrence relations, and I'm going to talk about a whole bunch of different tools that we can use in different settings to find some way of wrangling them into a form that's convenient to work with. Sometimes we need tedious proofs, but we want to find ideally a way of eliminating tedious proofs most of the time, and over time, hopefully develop a way of writing those tedious proofs faster.